Hi, my name is Anne Maria, and this is Physics Lab 5. The purpose of this lab was to collect observational data as the magnet falls through a conductive tube of aluminum foil, as well as creating a computational model of the magnet-tube interaction and comparing it to the observed data. The key concepts are the magnetic field of a dipole, which is formula shown on the right, and that EMF is equal to the change in flux, which is equal to the integral of the magnetic field dot product with dA, and an application of that is shown on the right. It was also important to recognize that if a loop has a conducting material, then the magnetic field or the change in flux will create an induced current. And then Lenz's law states that the magnetic field generated by the induced current is in the opposite direction of the change in flux through the loop, and that the magnetic force in a wire F is equal to current delta L cross product with the magnetic field. And Newton's third law states that the force on the magnet and the force on the loop will be equal in magnitude but opposite in direction. So the experimental procedure was to determine the north end of the magnet and then hold the aluminum foil tube vertically and position the magnet at the entrance, and then record the magnet entering the tube and leaving through the bottom of the tube, and to find the time elapsed for the magnet to fall and repeat 2 to 4 times to average the times for better accuracy. So then I created a computational model to show this phenomenon. I created constants for the situation, as well as the tube, inserting in the length, the width, and the general geometry of the tube. Then had a function that calculated the dipole magnetic field due to the falling magnet, and then the flux of the field and the change in the flux as the magnet fell through the ring. I then found the B field at the ring, which brought in the dipole formula from before, and then I calculated the forces, noting that F net is equal to the magnetic field plus the gravitational field. When I ran it, I found that the velocity graph is shown as one to the right, and the magnetic field, the magnet started at the top and landed at the bottom red. Computationally, it was calculated that the time of the tube was 0.333 seconds, whereas experimentally the time was 0.345 seconds, which is pretty close to the computational model. So the interpretation was that the red and blue indicate currents flowing in opposite directions, so either clockwise or counterclockwise. Here mine was red. So since the north end is pointing downwards and getting closer to the loop, the change in the magnetic flux was also pointing downwards. And since induced magnetic field points in the opposite direction of the change in the flux, we know that it points upwards and that the induced current flows in a counterclockwise direction. This could be found using the right hand rule with the thumb pointing upwards, causing the fingers to curl in a counterclockwise direction. And if the magnet is flipped, the current will flow clockwise, but the velocity and position of the magnet will be unchanged. So in terms of experimental versus computational time, it was very close. Improvements could be that there are no metals in the surrounding areas that would create external B fields, and that recording the video could be done in slow motion to have a more accurate time graph. Then for the velocity versus time graph, the slope is negative when the only net force is gravity, and when the slope is 0, the force due to the foil acts upwards and gravity downwards, so there is no acceleration, the net force is 0, and it reaches a terminal velocity. For the conclusion, if the resistivity is close to 0, we found that current is equal to EMF divided by R. So if R is very close to 0, then I will approach infinity. So since the force is IL cross product B, the greater the current, there will be a greater force. So the magnetic field due to the loop, which is an upwards force, will increase, so it'll take longer for the magnet to fall through. And if there were holes or slits, the ring currents would decrease since there's less area for magnetic flux to permeate through. So as flux decreases, EMF will decrease, I will decrease, and then force overall will decrease, meaning that it will take less time for it to fall through.